I join you at lunch. Antonis, I will be connected.
Yeah, that's fine.
Interessante.
C'è tantissima gente.
Avrò trovato. Assolutamente.
Just they'll have to move this way.
Yeah, sure. Yeah. Oh, sorry. Yeah, no. I'm at the very end. Yeah.
Yes, I find out. No, the microphone should stay. I think if you stay.
No, no.
Però sto molto bene in realtà.
Next week. This week and next week.
Yes.
Benissimo. In other parts of southern Germany. Okay.
Is that okay?
Black Forest. Io sono molto contenta.
Is the space in front of me?
Glielo voglio dire. Okay.
Instead, I seat, I think the slides still there.
Where did I mean that? So I can. You were asking where it is.
Yeah.
All right. Thank you. Let's start. One quick announcement I forgot to mention before. You probably know already because many of you registered, but we do have a Slack channel. At the moment, it's not structured at all. Probably we will make at least one channel per week for people just to follow up on talks and question. Yeah, let me know if you have some ideas of how to make best use of it. Otherwise, you can just use it as a place to post item for discussion of questions. There is also a social channel if you want to organize, dinner out or something else. So that's there for you. And okay, I think we can get started. The first topical review is about the census of AGN. And we are going to have Antonis, Sophie, covering the observational and the theoretical simulation side of it. And they will go one after the other. Yeah, exactly. It's okay.
So hello to everybody. Good morning. It's exciting to be here, and I would like to thank the organizers for the invitation to give this talk on the census of AGN. So my outline is that I will first motivate the subject. Why is it important to have a complete census of AGN population? And then I will move on to what I think is the current state of the art in terms of understanding observationally how many AGN are there. And in doing so, I will identify a number of observational challenges. And at the last part of the talk, I hope there is enough time to go through directions or thoughts how we can address these challenges, and inevitably this is connected with future missions or state-of-the-art data sets. But before I go to demographics, I would like to define a few quantities that I will be using throughout this talk. And the first one is this one, the AGN line of sight obscuration. And inevitably, in any observational talk on AGN census, this obscuration creeps in, and that is because we know that most of the growth of black hole growth in the universe is happening behind dust and gas clouds. We don't know what the obscurer looks like, but we know it's there. And in this presentation, I will use this quantity here, the hydrogen column density, to quantify the level of obscuration along the line of sight to the central engine. We can measure that through X-ray observations. You can see X-ray spectra on the far left, and those at the far right. And you can see X-ray spectra, model X-ray spectra with different levels of obscuration. And by modeling that, by using those models, we can constrain this parameter here. And of particular interest to this presentation will be the most heavily obscured AGN we believe are there, those that I will also refer to as Compton thick. They correspond to a hydrogen column density of that value, and an example spectrum is shown here. And you can appreciate the suppression of the X-ray flux compared to the unobscured case. And I will be talking about those in this presentation. Let me also say what I mean by demographics, how I understand this concept. For me, understanding having a complete census of AGN is identical to being able to estimate observationally in an unbiased manner the space density of active supermassive black holes in the universe. And you can express this space density as a function of a number of parameters, for example, accretion luminosity, redshift, hydrogen column density, level of obscuration. And therefore, you can build plots like this one, where is on the vertical axis of its panel is the space density, plotted as luminosity. This is also the luminosity function of AGN. The different panels correspond to different redshifts and different obscuration. Redshift is increasing from bottom to top. Obscuration, line of sight obscuration is increasing in this direction. And the different data points or shaded regions or curves in this plot correspond to observational measurements. We want to have an unbiased measure of that quantity across the lifetime of the universe. Towards the end of this presentation, I will also talk about extended AGN demographics, hopefully if there is time. And this is expressing the space density, not only as a function of parameters that have to do with the accretion process, but also as a function of parameters that have to do with the host galaxy, like stellar mass or star formation, even morphology. And this is a way to actually learn more about the accretion processes. Let me motivate why it is important to have a complete census of AGN. And the very first point is that we need to understand the accretion history of the universe. We see black holes at the centers of supermassive black holes at the centers of galaxies today. We want to find out when, during the lifetime of the universe, those black holes form. Essentially, ideally, we would like to have plots like this one, which is the black hole mass function at different redshifts. So the different curves correspond to different redshifts in this plot. And you can see how the space density of black holes in the universe is being built up from high redshift to the present day. And this particular plot is using the formulation, which is called continuity equation down here. But in order to produce such plots, an essential component is the luminosity function of AGN. If you don't have a complete census of AGN, these are wrong. Is that a question? Or? So moving on, feeding and feedback cycle of supermassive black holes. And this is demonstrated with this figure here from Melanie Habuzit's paper. I think Sophie will talk a lot more about that in her talk. But essentially, the point I want to make here is that if you look at the luminosity function of AGN, so this is the X-ray luminosity function, and what Melanie did here is that she overplotted on the observations a compilation of different of predictions from different hydrodynamical simulations. Those are shown with colored lines. And what you can see is that there is significant scatter, and this scatter is directly related to the physics going into those simulations for either accreting black holes or the physics by which black holes self-regulate themselves. And therefore, if we have an accurate measurement of the space density of AGN, we can possibly fine-tune those models and therefore learn about feedback. Another important reason for having a complete census is that we can then map AGN onto galaxies. So if we knew how in an unbiased manner, how AGN are distributed on galaxies, then we can study the environments or the physical conditions that are conducive to accretion events. Therefore, learn about triggering mechanisms. What is triggering an accretion event onto a supermassive black hole? If we were able to extend this mapping of AGN onto galaxies to very low stellar masses, then we can also learn about seeding in the early universe. And Things of E will also talk a lot about that in her presentation. Finally, if we extend AGN demographics to very high redshift, we can learn about the contribution of those sources to the ionization of the universe. And maybe this is a topic to be discussed in week 4 of this meeting. So this is the current state of the current status of what we know about AGN demographics observationally. I choose to use this parameter psi, which is not the luminosity function itself. It's not the space density. It's an integral of the space density, as shown here at the bottom. But the important thing is that by using psi, it is possible to overplot in a concise way observational constraints from different wavelengths. So this is why I'm using that. And this psi is plotted as a function of redshift. You can see different shaded regions, different data points, different curves. All those are observational measurements of the space density of AGN and eventually psi. And they are coming from different selection methods. You have X-ray, dominates. I'm an X-ray astronomer myself. But there are also infrared constraints there, and there is also information from UV optical selection of AGN that is included in this plot. And the point I want to make is that if you look at this plot, there is a significant scatter at almost any redshift, right, between the different observational constraints. So I will argue that the number one reason for this scatter is this one. We don't fully understand where obscured, in particular heavily obscured AGN are and what are their space density. So number one challenge for improving that figure is to have a better handle on the heavily obscured AGN. You can also see significant scatter at high redshifts, redshift beyond 3. We don't understand how the evolution of AGN, or there is a debate rather, on how the evolution of AGN develops after that redshift, but I'm not going to talk at all about that in this presentation. I think this is going to be discussed in week 4. However, what is relevant is that recent observations by JWST, which probe this particular redshift space, have shown that we have difficulty, or there are surprises rather, in how we identify AGN in low mass galaxies, right? And this is not a problem only at high redshift. This is a problem at low redshift as well. So a challenge that I will also discuss is how can we improve on that? How can we better search for AGN in dwarf galaxies, low mass galaxies, possibly going into the intermediate black hole mass regime. So let me go through those challenges and say a few more about each one of them, starting with the obscured accretion. The point of this slide is that, first of all, X-ray surveys, like Cosmos, for example, here, do find Compton-thick AGN, right? So this is work from Brivael, where he analyzed the X-ray spectra of AGN in this particular survey, and this one here corresponds to a Compton-thick AGN. The actual spectrum, the measurements are the blue data points. The black line and shaded region is the spectral fit, and those sources do exist in X-ray surveys, but because the obscuration is so high, the continuum, almost all the direct emission from those sources is absorbed, is suppressed, and we don't see it. And therefore, these sources are underrepresented in X-ray surveys. We only find a few of those, particularly as one goes to higher redshift. And that directly translates to uncertainties in understanding their numbers. And these uncertainties demonstrated in this plot here on your right, where you can see the fraction of Compton-thick AGN plotted as a function of redshift. Now, the fraction is defined as the space density of Compton-thick divided by the space density of the total galaxy population. And what you see is different data points, again, shaded regions. Those are the observational constraints from the literature coming from X-ray observations only. And you can appreciate the scatter, right? Even at low redshifts, there is a debate on how many Compton-thick QSOs, AGN, are out there. One way to improve on that is by using infrared wavelengths, selecting AGN in the infrared. And the argument here is that any radiation that is absorbed at X-rays here should reappear as thermal emission in the infrared, right? So there is this thermalization, and therefore, even the most heavily obscured AGN that are very faint at X-rays, they should appear here. And indeed, there have been many efforts trying to find AGN at these longer wavelengths, but this itself has a number of challenges on its own. Right? First of all, the dominant population of sources in the infrared are star-forming galaxies, and therefore we have to look for a small population, needles in the haystack, essentially. We have to identify a small number of AGN against a dominant population of star-forming galaxies. And this exercise inevitably has to go through decomposition. You have the SED of a source, like it's shown here, and you have to decompose the stellar component, which are those lines, from the AGN component, which is the red line here, right? And if you do so, yes, we can look for the signatures, the characteristic signatures of AGN in the SED and therefore identify them. However, any decomposition problem faces issues with incompleteness or contamination by non-AGN. Also, in the infrared, it's not possible to directly measure the line of sight obscuration. We need additional information to do so. And finally, the infrared selection is complex because essentially it is a contrast exercise. You try to identify AGN signatures against the background of star formation. However, what I am going to also mention here is that the decomposition problem requires a good understanding of how the SED of AGN looks like. And I think we have been realizing over the years that the SED of AGN is not universal, far from, actually. There is a lot of diversity in the spectral energy distribution signatures of these sources. And some of this diversity is shown here. So you have, for example, there's a debate on how cool the far infrared SED of AGN can be, or how hot the dust in the mid-infrared can be. And there are a number of papers here that discuss this diversity. And therefore, this diversity directly affects accounting for this diversity is important in order to be able to identify in an unbiased manner a QS AGN and obscured AGN in the infrared. Let me move on to the low mass, to the low galaxy stellar mass regime and how we can find galaxies AGN there. Now, this is related to the fact that JWST has been finding this population of sources here, the little red dots. They show broad lines, some of them, and we believe they are AGN, but they are at very high redshift. But at the same time, the surprise is that they appear extremely X-ray weak. So the X-ray weakness by orders of magnitude, in fact, is shown here. So higher values of this parameter mean X-ray weak. This is where most of the standard AGN live, and this is where the little red dots are found. Many orders of magnitude X-ray weakness compared to expectation. And the debate is going on whether, like, is that obscuration? Is that a weak X-ray corona? Are those AGN at all? And so there is an issue, and I also forgot to mention that the host galaxy of those sources have very low mass. They approach the dwarf regime. And if we go at the low redshift universe, so not JWST, but very low redshift dwarf galaxies, we can also look for AGN in those, right? And for example, broad emission lines, infrared signatures suggesting the presence of an AGN. And this is a paper by Ricardo Arcodia, where he used the ERAS-1 data, the Erosita All-Sky Survey data release 1 observations to look at the X-ray properties of those low mass galaxies. And what he found is that many of them are X-ray weak. So there is a large diversity in the X-ray power produced by AGN in this low stellar mass regime. And this X-ray weakness, again, is shown here. Unfortunately, the scales are opposite, so X-ray weak is down in this plot. This is where you expect to find typical AGN, and this is where many of those dwarf galaxies identified by either broad lines or infrared signatures are found. So there is an issue in understanding how AGN occupy, or how active supermassive black holes occupy the low stellar mass regime. Okay, so let me move on to the third part, where I will show some slides on what is coming in the future and how can we improve on some of those challenges that have been discussed. And I will start again with the buried AGN census and looking into the future, maybe 15 years from now. Athena will be flying, and hopefully on a similar time scales, this NASA probe class mission axis. And what I show here are simulations for Athena on the ability of that particular mission to detect Compton-thick AGN. I should also mention here that both Athena and AXIS, what they differ from state-of-the-art X-ray observatories, is that they have a very large collecting area. So that means that they can go deeper, but they can provide good quality spectra as well, X-ray spectra. And the modeling of those X-ray spectra can provide information about the line of sight obscuration, and therefore identify Compton-thick AGN. So what I show in these panels are predictions for Athena, the luminosity function of Compton-thick AGN, different redshifts at cosmic noon. The blue data points are what Athena is expected to provide, the uncertainties that Athena is expected to give. And these data points should be compared with a black line, the black curve. This is what is input in these simulations when it comes to the luminosity function of Compton-thick AGN. And the main point I want to make here is that a moderate exposure time with Athena, 200 kiloseconds, that's not a lot for X-rays, can constrain the luminosity function of Compton-thick AGN almost to the knee of the luminosity function, right? And that all the way to redshift 3. So hopefully Athena and possibly AXIS can provide a lot of information on the obscured universe. I would also like to advocate improvements, not only in data, but also in the way we analyze data, methodology. Because I have been talking about X-rays and infrared and how complementary the two wavelengths are, but I think what is missing is like a quantitative crosstalk between those two methods, right? How we can combine them, information from these different wavebands in a way that makes predictions about demographics, space density. And one possible way is shown here. This is the X-ray spectrum of a source in cosmos field. It's a very faint one, it's obscured. And those are the posteriors coming out from the spectral analysis. The vertical axis is luminosity. The horizontal axis is column density. And you can appreciate how broad those posteriors are, and they are almost bimodal as well. Right? And this is coming from X-rays only. Now, if you add to that information from multi-wavelength information, and in particular, information about the infrared luminosity of this particular source coming from multi-wavelength SED analysis, then you can significantly improve on those posteriors, right? And this is coming as a prior into the spectral analysis. You can significantly improve the posteriors, and this is shown here, where essentially this second tail of the posterior distribution is excluded. And I think we should explore more on improvement on method in order to better constrain the census, obscured census. This is certainly going to be relevant for Athena, but is also maybe relevant for improving existing observations. Another point I would like to make for the obscured universe is that, again, on methodology, on how to improve quantitatively the crosstalk between X-rays and infrared is forward modeling. And this is the exercise by which you develop an empirical model of AGN and galaxies in the universe. And then you use that model to make predictions, generate predictions, and mock observations. And in those predictions, any selection effects that may affect your data are part of the modeling. And this kind of approach has been used a lot to make predictions for future surveys or quantify the selection function of certain samples, AGN samples or galaxy samples. What I advocate here is that we can make empirical models, so forward models that include information about the spectral energy distribution of AGN. And then we can ask specific questions. For example, what is the selection function in the infrared of a given AGN type? Or do we find in infrared populations of AGN that are unaccounted for at other wavelengths? So questions like that can be addressed with this forward modeling. And an example is this one over here. This is a comparison between observations and a mock observation and real observations that are designed to test a very specific selection method for AGN. This is the selection method using WISE colors, WISE observation. So this is the WISE color magnitude diagram. AGN in this particular selection method are lying here at the top. And what you can see here at the bottom is what the forward model is predicting about the selection function of that particular infrared method for finding AGN when it comes to Compton-thick AGN. And the reason this is relevant, I think, is that because there's a Formos survey coming up, it includes infrared and X-ray selected AGN as targets, and forward models like this one can help interpret those observations. How much time do I have left?
A couple of minutes.
Okay, so I'll skip that and go directly here. So so how can we improve on the demographics on the low mass regime, low stellar galaxy mass regime? Well, there are a number of very interesting surveys, either starting or have started, or they will start in the near future, that will provide galaxy samples, large galaxy samples over large areas of the sky. We can combine those samples with X-ray information, for example, from Rosita, or in the far future with Athena, in order to study the incidence of AGN as a function of galaxy properties. This falls under the umbrella of extended demographics, where the space density of AGN is estimated as a function of parameters that have to do with the galaxy properties in which those AGN live in. And therefore, we can learn more about the incidence of AGN in low mass galaxies. An example of this exercise is shown here. This is combining the eRosita all-sky survey with the Sloan main galaxy catalog. And then you can estimate those extended demographics. They are not coming in space density. The units now is probability. So every panel here, the vertical axis is probability of a galaxy hosting an accretion event, with accretion power measured here by a proxy of the Eddington ratio. And the different panels correspond to different stellar masses, increasing from bottom to top. So here you are, this very first one is close to the dwarf galaxy regime or low mass galaxy regime, and the shaded regions correspond to the inferred incidence for the Sloan main galaxy sample for star forming and passive galaxies. This kind of study can be extended in the future to new data sets, extend the stellar mass range even more, and study the incidence of active supermassive black holes in low stellar mass galaxies. So I'll leave my conclusions here, and
we give the stage to Sophie. And mindful, we have a discussion time. So if you have more comments or items for discussion, keep them for later. But if you really have a question for Antonis about what he presented, now you can ask a question. Paul.
There sort of is, or maybe there isn't, when considering multi-wavelength assessment of your demographics, that a given, let's say, black hole mass and accretion rate, and I guess efficiency or spin or whatever, produces fundamentally the same signature across the wavelength. Now, to some extent, we know that that's not true because of the kind of scatter and all of the relations. But do you think that that's a reasonable assumption now? I mean, should you get the same answer if you're selecting, if you just threw away obscuration completely, would you expect to get the same answer?
so try to fit the same SEDs without obscuration, but with physical processes that produce the similar spectra.
Well, I don't know. I mean, are you assuming that you should get the same answer? I think we are all assuming that you should get the same answer, but when you take out obscuration, but is that a fair assumption?
I don't really follow. So the same answer as what?
From each waveband, from the infrared, the X-ray, from some correction.
Okay. Right. Well, I guess. Well, yes. My assumption is that you have an underlying population, you sample it with different methods, and with some selection function. If you understand the selection function well enough, then you get the same population. But of course, yeah, I mean, it's the key is the selection function.
So the little red dots or the dwarf galaxies suggest not.
Correct, yes, but and there's a big question mark, are those AGN? But definitely, I mean, if X-rays, as we thought up to now, it's a good way of finding AGN, and suddenly they are not anymore, then it's well, I don't know if it's a problem, but it needs to be accounted for.
One last question, and then
yeah, just a follow-up of this. I agree that yes, with the little red dot discussion, everything is quite new, but even considering lower redshift, standard search for the AGN population, and even considering fields that are covered by deep radio, mid-infrared, X-ray observation, then when you look at the population of AGN selected by the different wavelengths, even if the observations are really deep, the overlap between those that are selected only in radio, those that are selected only in X-rays, is not even close, maybe somehow, sometimes to 50%. So probably the effect of the different intrinsic SED of these objects is really something that is important to take into account.
And this is where sort of like modeling along those lines can help a lot, where you have some assumption about your population, some assumption about your SEDs, you produce observations, and then you compare with the reality, and maybe you learn something.
Okay, I think we already have some items for discussions later. Mara, do you have a quick question for Antonis? Or
very quick, Andrea, because I think it is relevant. In the plot where you were showing the black hole density, grow density, you were pointing out the scatter of the among the curves, yeah, but the majority of the X-ray surveys are actually using the same data. So it is just related to methods, or are you doing some different combination in order to have these different results from the various X-ray surveys?
Yeah, so some of those surveys that are plotted here, they don't actually fit for the Compton-Thick fraction. They assume a Compton-Thick fraction. Now others do, yeah, so there is this uncertainty, definitely. I don't think it's necessarily method. It's not necessarily how the data are analyzed, but it's what you fit for. And certain observational results that are shown here, they don't fit for the Compton-Thick fraction, right?
Okay. Thank you all. We will come back